A human life is a fraction of a second in geological time. Because our window of observation is so brief, the mountains and valleys around us appear to be permanent, motionless fixtures. Speed up the clock, however, and you see that every inch of the Earth's surface is a highly active, chaotic construction site. The terrain we walk on is caught in an endless tug-of-war. Deep tectonic forces slowly heave the Earth upward, while surface elements, water, wind, and ice, relentlessly tear it back down. The study of this constant physical reshaping is called geomorphology. Geology doesn't strictly happen in laboratories. It's an observational science written in the open air. Spotting specific physical patterns allows anyone to decode the violent multi-million-year history etched into the terrain. Observe a first forensic site, the Grand Canyon. Notice the vast scale and distinct horizontal bands of rock stacked one atop the other. These layers follow a rule known as superposition. The sediment at the very bottom settled there first, making it the oldest rock, while younger layers were deposited sequentially on top. But this presents a mechanical puzzle. How did a single surface river cut thousands of feet straight down through that ancient solid rock? Millions of years ago, immense tectonic pressures pushed the continental landmass upward. To maintain its path to the sea, the Colorado River had to grind downward, acting like a stationary saw as the rock was lifted into its blade. When a river sits inside a canyon this deep, it reflects a continent that was steadily lifted into its path. In high mountain passes, we see a different architecture. While water carves sharp, V-shaped ravines, this valley floor takes on a wide, smooth U-shape. That broad, sweeping curve remains as the signature of a vanished ice age. A creeping river of ice once filled this space. The moving glacier acted like giant sandpaper, dragging boulders to grind the steep mountainsides flat. This brutal downward pressure etches deep parallel scratches, striations, permanently into the bedrock floor as the ice advances. This serene, open mountain valley remains as a massive, fossilized footprint of crushing ice. On the flat plains, rivers naturally wander, snaking back and forth. Scattered near the main channel, we frequently find these strange, disconnected C-shaped lakes. Water flows faster on the outside of a curve, eroding the bank, while slower inside water drops sediment. This pinches the land into a narrow neck. A flood cuts straight across the neck. Sediment then seals off the old loop, isolating it entirely. These oxbow lakes are the architectural records of a river's restless, shifting past. At the edge of the continent, ocean waves act as horizontal sandpaper, constantly attacking the base of coastal cliffs. Yet the most dramatic coastal destruction, entire bluffs collapsing into the sea, is often triggered by an invisible culprit attacking from the inside, groundwater. This diagram shows the subsurface mechanics. Rainwater sinks through loose soil until hitting a dense clay barrier. Pooling water flows horizontally toward the cliff. This adds massive weight while lubricating the soil beneath until friction fails and the cliff face shears off. While waves batter the exterior, coastal collapse often results from a structural inside job, driven by the immense weight of water pooling quietly underground. Having learned to read these signs, it becomes impossible to view the landscape as a collection of static rocks. The tools of creation, water, wind, and ice, are never finished with their work. Even at this exact moment, the ground beneath our feet is being quietly dismantled and reshaped for an era we will never live to see. The next time you look out an airplane window or stand at a canyon's edge, you are observing an active construction site. You are reading the autobiography of the Earth.